Hello, and welcome to your short introductional video on geopolymers and rammed earth. So is it possible to make concrete with no cement? Well, it turns out it is if you start with a highly alkali solution, a source material, some aggregates, you mix it all together, you cure it, and you end up with something like concrete called a geopolymer. But it's really important that we focus on what is this highly alkali solution and what are these source materials. According to this picture, we need something from a coal-fired power plant. And yes, we already know that we can get fly ash as a byproduct, right, from burning coal, but that's only one possible source material for geopolymers. Another thing that works is a granulated blast furnace slag that comes from the production of steel, another byproduct. And it turns out that actually a mix of the two of these together in a 40-60 ratio, or somewhere in between that, and 40-60 of either material being the larger of the ratio, actually does much better than a mix that's 100% fly ash or 100% granulated blast furnace slag. But kaolinite clay, which is a natural resource, right, naturally occurring mineral, that's also a really great source. And so what is it that all of these have in common? Well, they all are high in silicates and aluminates. And that should actually sound familiar to what are the ingredients for the base materials for making cement. So we need those silicates and aluminates, and that is part of what creates the polymer chain for us in our geopolymers. So we're going to go back to our image. And so we now know our source material isn't just from coal-fired power plants, but could be the granulated blast furnace slag or this kaolinite clay. But then we also need this highly alkaline solution, and you see the sodium hydroxide and sodium silicate ingredients mixed together, and what we're really looking for is something that's a sodium metasilicate alkali. Now, if you remember by alkali, that means we have a really high pH, and we're talking high enough that it is caustic. This is something that when you mix, it's dangerous. You are wearing goggles and big rubber gloves and vests, whatever, to protect you and your skin, because the alkali solution can severely burn your skin. You mix it with standard aggregates of sand and gravel, and then you cure it. Now, we have really low heat of hydration, and in fact, curing in an oven actually improves the quality of the geopolymer, or at least speeds up the strength gain. But you can cure this at ambient room temperatures, and especially if you want to do any sort of exterior construction where it's kind of hard to get an oven inside. But if you are a precast factory making precast panels or any other precast beams, columns, whatever, if you have the ability to add heat to the process, you actually can create a better product or speed up your process. But what you end up with is a material that looks an awful lot like what we're used to for concrete. And in fact, here are some samples. On the left, we see a fly ash based geopolymer. In the middle is kaolinite. I'm going to come back to that. Next to the kaolinite is our granulated blast furnace slag. And then we also have a traditional Portland cement concrete cube, and the fly ash, the blast furnace, and the traditional concrete look pretty much the same. Now the kaolinite, often there's an iron based in that, and it gets you that kind of red color sometimes, but it's really strong. And we actually have kaolinite in our structures lab, and we have some cubes in the lab that you're welcome to check out next time you're in there. And we have opportunity to mix this material. We do have both the alkali additive as well as the basic silica ingredients that we need. And what really happens is that alkali solution gets in and polymerizes the silicate aluminate material. And when it does that, it turns it into molecular chains and networks that create this hardened polymer, where a polymer, right, is repetitive chain of something. It creates this binder, and the binder tends to be much denser than regular Portland cement. Here's a zoomed in photo, and in the upper we can see our Portland cement. It's a rougher material versus the smoother, tighter mix of our geopolymer. Now, there are many advantages to the geopolymer. We've already listed some of the discussed, I should say, some of the disadvantages in the caustic material, and that you might need heat to make it a little stronger. But This structure here just shows off one of the things that you can do in its beauty. So this is a Global Change Institute that was built in Queensland. It was the first geopolymer concrete structure, and they also have these precast concrete panels as part of the structural facade. And they were able to use different types of clays, different kaolinites with different coloring system to it to actually create the beautiful coloring in the panels. So that's one advantage. But some other advantages are no cement. But, oh, this stuff is strong. After 28 days, on average, you're getting about 10,000 psi strength, or 70 megapascals. I want you to think back. Lab tests and lab mixtures were 3,000 to 4,500 psi. So 2.5 times the strength of regular design. And high strength concrete is usually considered 6,000 to 8,000 psi. So this stuff's strong. What's amazing though, and we have done this in the lab, is within 24 hours, you can get almost 4,000 psi in 24 hours. So if you need to do runway repair for an airport or freeway repair, think of the strength that you can get without anything special added to your mix. And you can make these even stronger if you need to. This is sort of your standard mix. Because it has that tighter polymer binder, it tends to be less porous than regular ordinary Portland cement concrete, and with that it's going to be then more resistant to your different chemicals coming in to attack it. Be aware though, if you make it with just granulated blast furnace slag, that tends to be more porous than the ordinary Portland cement, so you don't get that advantage. And you can get some alkali reactions occurring. We already said it has low heat of hydration. One of the things that is interesting is we think of concrete as being fire resistant, and it is. It's not flammable, it has resistance at some point, but it will fail in fire, and it tends to be a little bit of a catastrophic failure, and the geopolymer has a greater resistance to that than regular ordinary Portland cement concrete. So that's your brief introduction to geopolymer. There's still research that needs to be done, but it's an exciting product, and I encourage those of you interested to take some time and look a little deeper into it. But we're also interested in rammed earth. So rammed earth also can be made beautifully, and it takes advantage of natural materials. And so we know that we can build tall with it. Here is a almost 100-year-old 7-story rammed earth building in Germany, but it's very old material. It's been around a really long time, over 1,000-year-old castle in southern Spain. It's also part of the Great Wall of China, so we know it's been around. It's an old technology. Now, when we're normally building in these older traditional buildings, we're talking about clay and sand, maybe a little gravel, but clay and sand are your main ingredients, and you usually need about 30% clay. Clay is the binder, and that ratio that you have will affect the finished product. You want to mix it to a certain moisture, and so that it makes it easier to compact and hold its form. But when that clay hardens after it's been wet, then you get your wall performance. Now, stabilized rammed earth ends up being using cement, and we add cement, and in fact it's required in California to do our seismic considerations. And your cement typically replaces some of the clay, not all of it, but it will replace some of the clay, and when you do so, you end up with about 8 to 10% of the wall weight being cement. Now, if we reflect back on the concrete mixes that we did throughout the class, in those, if you went back and ran the numbers, you're somewhere maybe 13 to 16% of your batch weight being cement. So there's more cement in that mix, but if you add any pozzolans at all and remove some of the cement, you're kind of getting close to using the same amount of cement in a rammed earth wall as you are in a regular concrete wall. So that's a little disappointing, and even though it's a lower percentage, your rammed earth walls tend to be at least 2 times thicker than your concrete walls. So in the end, you're using the same amount, if not more, cement in a wall. Also, it typically is considered very green because, oh, you just use the soil right from your site, you dig up your foundation, you now have your soil to build your walls. And while that can happen, and that does happen in places, in your developed countries, clients typically want neat colors and striations, and you might not have the right soil on your site, and it is very easy to ship soil from pretty much anywhere you want. And so we lose that local material benefit because of this, how easy it is to ship soils from different locations, which does happen a lot. So the basic idea of rammed earth is we have a formwork, we put in some moist soil that's going to have our sand, gravel, clay, and some cement, and then you just pneumatically tamp it. And as you tamp it, that will harden basically into stone. It won't be pervious. You can spray it with water. It's pretty impressive. You come back with a new layer and you keep tamping. But what's missing from this diagram is that you actually have to have reinforcing bar, and now most of your walls have integrated insulation. So it'd be really fun to see what that looks like. So here, looking at this beautiful rammed earth structure that's up in Napa, let's see how the actual process of construction works.
Some things haven't changed. Soil still forms the basis for making rammed earth walls.
We're using the material that comes from beneath the topsoil, and we're careful about our soil selection, and then we compact that. Okay, we're standing in the formwork, and we're going to put some foam in.
And that's the insulation.
That's exactly right, yeah.
Okay. Mira Krajinoff has adapted the process by insulating and strengthening the walls.
And then we take some steel. I was excited about doing rammed earth, but it needs to be insulated. So we thought insulation, let's hide it in the middle, because the beauty of the rammed earth on both sides is, a good attribute. We put the soil in on either side of the foam and compact it.
The rammed earth walls are tested for strength, and the results indicate that they will be standing for a long time.
We take a diamond drill and drill out a cylinder like this, which goes to the geotechnical lab and then gets crushed. And that's how they determine the strength of our walls. And normally the results are twice what the engineer expects. So our walls are extremely strong.
How do we know it just won't wash away with a lot of erosion?
Well, let me show you.
Water does not penetrate a rammed earth wall, so it leads to healthier indoor air quality. Looks pretty good.
And so that's your basic introduction to also rammed earth. You've seen geopolymers and rammed earth. These are some traditional alternatives to concrete walls, and I hope you get excited about at least one alternative material and take some time to check it out. Thanks for watching.